It's very nice to be back in Seattle at INT, and it's of course very interesting to hear about this nuclear structure and things like that. So, I mean, Govert gave a talk in the first week, so it's kind of this. Well, a lot of this is simulations from Triactum, so this is all done with Govert. Giuliano, we're now collaborating with neon and oxygen collision, so that's kind of this light ion laboratory. He gave me the title, in fact. So last week I also gave a talk, so there's a little bit of overlap. So also Juliana said maybe go a little bit into more details about the Bayesian things, but then in the end I have a lot of oxygen and neon results, which I think is the main focus of this talk. Yeah, there's also a little bit of overlap with Govert's talk, but okay, since the audience completely changed, I think that's not really a big problem. So the idea about these heavy ion collisions and global analysis, or like Bayesian analysis, is well, I'll say a little bit more about it. I don't want to go into all the many parameters. There are like 25, so to really fully explain that model, you can ask me. So there's a lot of experimental data, and of course that's kind of the problem here. Like many of these parameters are of course physical, like shear viscosity. But many of them are also phenomenologically, so we don't really know how the entropy and the energy density kind of get translated from a collision. And all of these parameters, they kind of involve non-linearly the experimental data. So it's very difficult to kind of look at this elliptic flow, which we saw many times, and to estimate the viscosity, because all the other things also affect this kind of elliptic flow. So that's why you kind of do this global analysis, and at least that's the way we attempt to do it. So I'll start a bit with recent lessons on the shape of nucleons inside the nucleus, because this is something which has been really crucial for also our understanding a little bit of this Bayesian analysis. So it's really, so there's a particular point here, the net total cross section, which is also very relevant for this neutron skin I talked about last week. And yeah, so this total cross section kind of just determines, of course, the size, and the nucleon width really influences that. So I'll say a little bit about that, and then basically just go to these results for oxygen and neon. Good. So Triactum. So we're of course very proud of this. It's a public heavy ion code. You can all download it. It's supposed to be very okay. I'm not very good in this mouse thing. Oh. Okay, yeah, so you should point it first and then it kind of, okay, if it feels more natural. Anyway, so this was Govert's PhD project in Utrecht. So Govert is now at MIT, of course, and I was at that postdoc at that time in Utrecht. Well, we really put a lot of effort to make it really fast. I mean, at least Govert says he can now run 1 event per second on his laptop, so that's really quite nice. And you really a lot of efforts put to do everything exactly precisely as an experiment. So we can really do also, because it's very scalable, so it's parallelized. So for instance, the centralities, they will be done exactly the same as an experiment. And I'll actually show you one example where this really matters. The name comes from the old Utrecht, and Triactum sounds a bit similar. It's called bridge in Latin. I think it's the old Roman name of Utrecht. So the standard model of heavy ion collisions really involves like basically 3 stages. So there's the initial stage, there's the hydrodynamic stage, and the hadronic gas stage. So the number of parameters we have currently in the model, and that's actually increases over time, unfortunately, or maybe it's actually better. So the initial stage perhaps the most unknown, because okay, of course, this collision is a very non-perturbative process, and there are some first principle computations from like big liquid couples, like color glass or epiglasma. There were some experts, well, still are experts in the room. In our model, we don't really do that, so we're a little bit more agnostic, also because many of these energy scales are actually such that QCD is strongly coupled. So in a way, I think one way to view this is that if everything goes well, we should reproduce what the first principle up initio or something like that give for these kind of parameters. And these are actually 2 real examples that come out of our Bayesian analysis for the initial energy density for the hydrodynamic model. And so you already see that these are very different. I'll say a little bit more about that. So this one has much finer structure. So every nucleon, for instance, can have constituents. It's a parameter. The constituents have a certain width parameter. The nucleon width is a parameter. So then you can imagine that this adds up quite quickly, and that's why these look so different. I'll say maybe a little bit more about it. So then there is this kind of non-thermal flow. So that's actually quite important. So at some point you switch to hydro, it's a parameter. So at some time, say 0.5 Fermi over C. But before this 0.5, of course, these things, they don't stay still. They also kind of move out, and they move out in the direction of the gradient. And so we have like a hydrodynamized initial stage, which unfortunately I don't have time to talk about, but this is what Govert talked about. And what is also very important, I'll come back to that a little bit, is that so even if you have like a single nucleon collision head-on, say, and then you have this energy density profile, still the amount of entropy it produces fluctuates according to a gamma distribution. That's also very realistic. I mean, imagine you have a proton-proton collision, and of course, not every proton-proton collision gives the same number of particles. Now that also fluctuates, and but this is a very important parameter, especially related to the nuclear structure, because the more fluctuations you have, well, V2 changes in like central things or something like that. So it really is kind of a similar effects to having like a smooth or less smooth nucleus like oxygen or neon, which is an important one. And yeah, in the model we have like 4 parameters for shear viscosity because it really depends on the temperature. Although I have to say that we're mostly sensitive to the average value and the slope. I mean, the other two, we just don't constrain very well. So maybe we're a little bit optimistic here. Second order transport coefficients are actually quite important. So that's something which is quite new that we get to, that I also don't have much time to go into, but it's not very relevant for nuclear structure. We talked already quite a lot in this week and maybe last week about this hadronics cascade code. So Agnieszka talked yesterday about it, like your QMD or SMASH. And there's a bit of uncertainty there, which we don't have much control over. So triactum is all written as one executable, but SMASH is still separate. So the 2 separate codes, and there's one parameter. Actually, there are 2 now. So there's one parameter which is like the freeze-out temperature. So at some temperature, you really convert your fluid in thermal equilibrium to particles. That is already quite complicated by itself because this fluid is not isotropic. So the pressure is not equal in all directions. So if you naively convert it to particles, then of course thermal Boltzmann distribution would be isotropic. So we actually have to apply a rescaling in certain directions, such that the pressure, which is higher in some direction, there are more particles moving in that direction. So you do this to kind of exactly match the stress energy tensor. Yeah, and then this SMASH code takes over. So that's kind of a little bit outside of triactive.
So can trajectory be run in just 3 different modules? So can you just do initial stage with trajectum and then do something else for hydro, or just do the hydro with trajectum?
Yeah, so we explicitly did like Jetscape has this kind of modular thing, and triactum does exactly the opposite. So it's a single executable. So it's not possible. So at least not built like, I mean, these initial statements we have like Trento, but we also have like Monte Carlo Glauber. So we try to kind of, we have different options for the hydro kind of things. Okay. So within triactum, you can change settings. Like oxygen, you can add things like that. And it has advantages, right? Because if you have these different modules, well, I think it's mostly the speed and the scalability. Everything works very, once you run it, we more or less guarantee that the result makes sense. So that is, that's the idea, the philosophy, at least. So this is indeed how it looks like. I think I showed it last week, but okay, it's such a nice movie. I'll show it again. So you have this initial condition, and of course it cools very fast because the longitudinal expansion. So it's really transverse direction, and longitudinal expansion direction is completely decoupled. It's very different from nuclear structure. And something I emphasized last week is that you have this initial elliptic shape. Okay, wow. So it's an elliptic shape, and the particles really go more in the direction of the short axis than the long axis because the gradient is bigger in that direction. And here you actually see that all these particles, they ended up in these directions and not so much in these directions. So it's kind of a visualization of this effect of elliptic flow. Well, one thing, okay, which is quite relevant for these isobars and all these kind of things, like in the triactum parameter file, we have this entropy acceptance probability. So what we do is, so in this case, this particular case is for this event. So here I put like everywhere 0 except between 24.5 and 25.5, I put a small probability. So what it does, it will generate many Trento events, compute the entropy, and it will only take the event which is at 25%. So this is it's just one event, it makes only one event, but it's guaranteed to be a 25% centrality event according to the entropy criteria. If we do a real simulation, we don't do, of course, only 25%, we do everything, but we can still kind of put more events in some areas of the entropy. And of course, if you put more events there, it's not that we take centrality from the entropy, because that would be, the centrality is measured with multiplicity, so that would be incorrect. But we take more events, like for instance, the 0 to 1% entropy one, and these more events, of course, they get a lower weight. So it's just a weighted way. So in that sense, it's completely guaranteed to be correct, because once you then, of course, because entropy and multiplicity are tightly correlated, once you do this, you're very likely, at least in the 0 to 1% multiplicity bin, to find many of these low weight events. So it improves your statistics a lot for this kind of central effect. It's kind of how this kind of particular feature works, and I'll show several examples where we actually use this very efficiently. And then to show, well, so it's more like, yeah, so I'm a little bit sorry about this. It's, the whole presentation doesn't have many formulas, it's just pictures to show you like what it looks like. Could have done it in formulas, but I think then in this case it goes a bit faster and you get the idea. So these are actually also these 10 kind of different settings, but all these settings, they are actually probable settings according to the Bayesian analysis. So this is not just some random parameters, which is usually what, so that's what we do first, right? I'll say a little bit more, but so first some random parameters, basically, then you tune the model to the data, and then you get the probable settings. And these are the probable settings. And it shows a bit what's the wide variety and how the shapes looks like. I actually put the parameters, so you see these widths, so they're quite small, like from 0.45 to 0.6. So that's kind of the range you can do it. So you see this 0.45 is definitely smaller than the 0.59 one, and you can have different constituents. Well, these ones are selected at different centralities, but this is just a single nucleon. So it's okay. These are so they're pretty round, but okay, depending on the number of constituents, it doesn't have to be very round. Then you, of course, put many of these nucleons in a lead collision. And here I already kind of I'm only drawing the nucleons that are what we call participants. So you have like a collision of lead on lead, and some nucleons hit another nucleon according to the nucleon cross section. And if they hit another nucleon, then they participate in the collision, and then they form some plasma. So there are several steps. So first of all, it's the nucleon. Then here there is the whole nucleus, and then of course there are two of these nuclei, so the left and the right moving one. And so then to get to the energy density, you need to combine these two, and we do this with this kind of Trento formula. So it's basically the entropy density basically feels like square root TA TB, with the A being the one nucleus and the B the other nucleus. This is the result of the Bayesian analysis, so it could have been square root to the power 1.4. That was a result. And so what's quite important here is that, so these are also different initial times. So for instance, you see that if you have like very early times, then you kind of have a lot of the structure left. Like this one is very fine structure. It's very early time. You see it's very fine structure, so quite different. Then for instance, this one also has a very small width, but then since it's already quite a late time, it already kind of moves away, and then it kind of smooths out over time. So this is kind of included in these initial energy density profiles. And I just took like, I think 100 events, I sorted them, and these are ordered again, I think by multiplicity or by entropy. And so just to have these different centrality classes.
So, so when you say 10 probable configurations, you mean all of them reproduce the experimental data?
Yes, yes.
And when you choose these configurations, is there one that's like dominant or more important, or like do you have a way to figure out which one that's impacting the choice of the other?
The choice of the others?
Yeah, like are the other parameters dependent somehow on one parameter? Like for example, the initialization time.
Yes.
We know that that one affects almost everything else, right?
Yeah. So that's a very good question. It's basically correlation between these parameters you're asking, right? I think in this case, I have it in the backup slides, how this is exactly looking, but there are many parameters that are pretty highly correlated. For instance, what's kind of well known, if you take a very small fine grained things like this, you get a lot of radial flow. So you get quite a lot of mean PT. So basically what you kind of need to do is to make the bulk viscosity a bit smaller, larger, to compensate for that, to get the mean PT right. So these correlations are definitely there. Does that answer the question or not? No.
Yeah. So I think my question, are we biased to the choice of these parameters? Are we like, do we have control on what, like to select one of these parameters or not?
Yeah, so basically what this Markov chain Monte Carlo does is he just generates a list of like 10 million parameter settings, and all of them are equally likely according to base formula. So you can just take any of these millions of parameter settings, and the theory is that are equally likely. But of course, what you're not supposed to do is take the width from this one and the time from this one and the constituents from the other one. So they have to be they have to be consistent with each other because they're correlated.
So we have like some physics background to select or avoid one of them, some of them.
So that's also a very good question. So this Bayesian analysis, I might come a little bit more to it, but not much. There's a prior probability. So indeed, so for the width, for instance, like the Jetscape puts it quite high, but for instance, the Q group say, well, we take the width only to 1 Fermi because we know from the charge radius, if you have a Gaussian of 1.5 Fermi, your proton looks like this. It's 1.5 Fermi Gaussian width, so the proton would be 5 Fermi. The Duke group says, we know that's ridiculous, they put a prior. So that's a physical choice. So it's kind of really what you're referring to, but you don't have to do that, and then you can write something in a discussion about it. For all of that, I mean, usually there's very little we really know for sure. Like this width, I think, is a good example where we probably know. In the Duke group, they also said that the eta over S has to grow with temperature. And the reason is that asymptotically high temperatures, the eta over S is weakly coupled, and you know the eta over S is very, very large. So it has to kind of go down when you go to lower temperatures. But this is the asymptotic high temperature result. And actually, the same arguments can be made at lower temperatures because hadronic resonance Gauss is also quite high. So we don't do this anymore. We also allow negative slope because at low temperature, I think the slope can be easily negative and it can be minimum at like 300 MeV, and then it can go up again. So this is an example where we change that prior. But all of these, they just take a flat prior in some range. I mean, we don't have very sophisticated knowledge, we think, and that's why it's flat.
Yeah, I was just thinking that if you do any filtering after you get the configurations, then you do filtering based on these physical assumptions to kind of get rid of any inconsistent parameters, for example, as you just said, nucleon width was the initialization time, for example, or eta was the temperature, any combinations that should not be allowed.
So we don't really need to do that, I think. We don't find any real inconsistencies after these things. So that's it.
You remind me, what is the third floor?
This is the sub width. So there's like constituents, like 5 in this case, and this is the so W is the real width, and I don't. It's not so clearly. Yeah, I was making these plots, and I hoped you would see it very clearly, but no.
So NC is the number of partons per nucleon or something.
Be very, very careful to say the number of constituents because it's not supposed to be quarks at all, right? Okay. I mean, quarks they just fly off. I mean, these are all gluons. And then it's a phenomenological parameter that determines the substructure you can have.
This sort of parameterizes how much shape fluctuates.
Okay.
If you want to be very agnostic about what it means microscopically.
So NC large means it's nice and spherical.
Yeah, there's less fluctuation in the shape. If it's smaller.
No, if NC is 1, then of course it's
one special, but
okay.
Otherwise larger means less fluctuation, and
well,
smaller is more fluctuation.
One update we did regarding to Duke is if it's like 1.38, it has a 38% chance of being 1 and 62% being 2. So it makes a continuous parameter, which is much nicer for the statistics.
So the most deformed shape would be n equals 2.
Then you would get automatically quite elliptical, yeah.
The largest fluctuations in the sense of the shape, right?
Yeah, I don't know if it's there.
Yeah. They're all fluctuating independently. They have random positions. So if you have 10,000 of them, then the shape will not fluctuate very much.
Question. The first row, number 3 and number 6 have both W.51.
Yes.
But they are different. What do they differ?
The number.
The first row, panel number 3 and panel number 6 have the same W, but they are obviously different.
Yeah, so it's definitely the time. But
These are parameter sets, 10 of them. So each column is a set of parameters.
No, but which one here? Number?
The top row, 0, and then I go to the third column.
The scan. Yeah, these points 51.
So why don't they differ? That's what.
Yeah. So this is probably the step wave is also very similar. The INT is also very similar. So it's most. Well, no, the third one and the sixth one they're very similar, right? But they also look quite similar, right? I think this is just random.
Okay.
That these could be the same. They're interchangeable. But one thing I'm also a bit confused myself at some point before I drew the time is that I think this, for instance, this point 46 and this point 41, they don't look the same at all. And it's really because this one starts at point 27 and it's point 62. So it's a snapshot at a different time. So this one actually would evolve similar to this one. But you see some, if you zoom in, you see that this one is coarser than this one's smoother. So it makes quite a bit of a difference.
Okay. These are just 10 random samples of a posterior, right?
Yeah.
So you could have two of them that are almost in the same point in parameter space, just
How do you decide how distinct those configurations are, if they're very actually similar? Like, can you put a criteria on how?
No, you just look at it for a long time. This is an illustration. But it's a real conversation.
But if you have many that are similar, you're gonna have a probability distribution of the end, right? So then you're gonna have like a peak.
Yeah.
in that.
if it's sharply peaked, then all 10 will have almost all the same parameter values.
Yeah, of course you can look at these from.
So clearly there's something favorable.
Yes,
to
that's
the-
nice.
than which one.
But okay, I didn't do that so specifically for this one. Yes, okay. So I wanted to say few words about what we really do in this Bayesian analysis. So it's actually really quite simple, and it's also, I don't know if people are more probably as nuclear structure and people are not more familiar with these LIGO things, but it's of course true that they're LIGO, they also have these waveforms, and they also use an emulator because it's very expensive to compute these mergers. They also have like different masses, they have different angular momentum, different inclinations, and all these things are very correlated. It's one of the reasons why you cannot easily with LIGO see the distance between the merger, because the distance is very correlated with the inclination. So you can get a very tight constraint on both of them, but not like this. The distance is the inclination. But yeah, and then the distance is very uncertain, which is very unfortunate for them. How you do this is really, so I said already a little bit about this prior. So this is BX, which we don't know so much about, but the idea, of course, that if the experimental data is really tight, then the prior doesn't matter much. In this case, not so clear how close we are to that. Then the probability is really of some parameter x. So it's a multi-dimensional space. It's really just like, what are your data points at x minus the experimental data points? And it's just a chi-square. So this inverse sigma is really the covariance matrix of the uncertainties. So on the diagonal are really just the uncertainties, the experimental points, and the theoretical points. And and what is very important, and we stress like very often, is that actually these correlations are very important, especially if you do many data points, which you do, and they're very related, like different centrality classes, different PTs, they're close to each other, so they're very correlated. So it's very important to take that into account. Experimentally, it's a little bit difficult. Theoretically, okay, so there are two uncertainties which we take into account theoretically. So at least the way I see it. So the one uncertainty we take into account by having the model being very flexible. So you can have many of these subwaves or the parameters. So it kind of offers some flexibility to kind of to parameterize the things you don't know. The second systematic uncertainty we take into account is that we don't really compute at every x point this formula. No, we use an emulator. Because it's so expensive to compute. So actually we run on like 1200 design points, or currently actually 3000 for the newest run. And then you use these Gaussian processes to predict all your observables outside of the design points. We have like 653 data points, and these Gaussian processes are really great. So you use principal component analysis first. So because of the principal component analysis, you know the correlations, and you know also the uncertainty in the emulator. So that is fully taken into account. And then, as I said, you do this Markov chain Monte Carlo, you get like 1 million probable parameter settings, and then you compare the posterior with the data. So let's see, so how does it look like? So this is actually the raw output of this kind of 1200 points. So you have all it, and actually see, so you actually have to kind of look at it at some point to see like if your data points are like nicely within the band, like if they're on the edge, and you know your final results will not be that great. And then, yeah, so basically what this Markov chain Monte Carlo, it takes all these parameter sets I just showed you, the 1200, and then it finds like areas in the parameter space where it nicely goes through. And for almost all of the data points, we do a pretty good job, although there are some notable deviations that are also significant. And also what you can see already from this plot, so something like this V2 is very important. So it's the red one over here. And you actually see the experimental assert is very, very small. It's actually only like 1% or 2%. The band is much wider. So you could wonder like, okay, why doesn't your Bayesian analysis not select the parameters that go exactly through instead of like being like really much too high? And here the reason is really the width of this band is set by the emulator uncertainty. So it's just that our model doesn't, as a function of the parameter, cannot compute this V2 accurately enough to really tell which parameters are really likely there. So that's really consistent, but it's of course also something we as theoreticians have to improve upon.
One question about your mean PT.
Uh-oh.
Because there are different calculations for mean PT, why it's different ways. Why is the classical spectral analysis you do mean PT based on the average of many particles of many bands? The other is what we do mean PT calculations. Every single band, and then you have to weight the average based on the principle. Those numbers are not necessarily identical.
The mean PT in a certain centrality class is just you take all the particles in the centrality class and you average the mean PT, right? You average the PT to get the mean, no?
Do you have any additional weights?
Definitely not. And if Alice does so, then they might be wrong.
For spectral analysis, we didn't. Guess the same with what you got.
You cannot, right? I mean, the definition is just, it's the same as the multiplicity. You just count the number of particles of all events in the thing, and that's it. I mean, we have discussed this before, and at least for instance, this V2, there are some funny weights here. Okay, you can switch to Atlas data, which doesn't do that. But no, you should not wait there.
What weights do you put in when you measure
From
mean PT?
UPT, yeah.
I didn't quite follow this.
So for example, if there's a mean PT, there's also mean PT calculation.
Yes, that's a different observable, yes. Yes,
And there you might have some consideration with the multiplicity
yes.
and apply a multiplicity as a weight.
Uh-huh.
Because this is something we use for Pearson correlation purposes. PTT has three particle correlation such as weight for mean PT.
Yes,
And for this mean PT, it's a different mean PT calculation. You don't apply any weight.
right.
That's just one group.
Okay. For
Yeah,
me,
these
I
ones-
imagine it's very insensitive to weights. It probably would hardly change actually, but anyway.
I mean, PT should be, well, like, yeah, you
I
can,
mean, which
there,
one?
of course, there's this fluctuation in mean PT. So if you weight the high mean PT once more than low mean
No,
PT,
he's
for some
weighting
reason,
multiplicity.
he's weighting
So
the
within that
multiplicity.
bin, like multiplicity doesn't even vary that much, and if you weight high multiplicity within the bin a little bit more, like BPT doesn't change that fast, like I
I
can't
think
imagine.
for
it-
this case, probably true that this would not even matter. But for the PT fluctuation, or for this row observable I show in the next slide, it makes a lot of difference. And yeah, and at least doesn't really, for instance, they don't write down what they do, so you always have to ask them, and then they.
Yeah.
Do you know why you always submitted ET data?
Yeah, well, I mean, these measures are always right, but so this is not possible, right? Because this, well, I put this posterior over it, but this is the multiplicity. Multiplicity is exactly right. This is the mean PT.
Yeah.
The mean PT is a little bit too high. That's admittedly too high, like 4%. So there is some correlation there. But this one is 20% too high.
Yeah.
So you cannot have the multiplicity right, the mean PT right, and the transfer, and it's just inconsistent. But I talked about these, of course, with them, and well, I mean, this. So they say you have to treat this uncertainty very seriously. So it could be really, if it's within 2 standard deviations, then you're good. So, and also these uncertainties, they're really not that correlated. So, like for instance, also if you really look very carefully, like this d and the eta. So we know quite well these are all the charged particles. But then here there's the multiplicity, the pions, the kaons, the protons. These d and dy, but okay, we know really quite accurately how to convert the dy to the and the eta. It's Jacobian, but we know it very accurately. If you convert these pions, kaons, protons to the and the etas, you add them up, you don't get the and the eta. So, and of course you can correct a little bit for lambdas and all that, but they're different detectors. So you really have to take, if you then ask them, you really have to take the uncertainty very seriously.
Is there any extrapolation to zero PT or anything?
Yeah, but that's included in the uncertainties.
So you enforce the agreement with the multiplicity and relax the others in order to do it.
No, this is a result of the analysis itself. So the analysis really wants that multiplicity right and the transverse area not. We also use the spectrum, so there's a lot more data in this. So if you really take the Bayesian analysis quite seriously, it suggests that the ET measurement might be somewhat off. Also, what you see quite nicely here, what works very well, this ET actually has like many data points. So you would naively think that the Bayesian really wants to fit it because there's so many. But no, they're all very much correlated and it doesn't care. So it just gets a single penalty, the normalization of 1 or 2 sigma in the chi-squared. So it doesn't get for all the data points. So it works quite well.
Is there a correlation between the mean PT and the spectra, for example?
Experimentally, we don't put that in, but in the emulator that comes automatically out of the principal components.
Sure, but it still means that you're sort of weighting that more in the to get the posterior, right? Like it's more important, right? 'Cause you're
Yeah,
sort of
so I
adding-
mean,
you're adding
Joe-
more data points that aren't correlated.
Well, it's a very good point because that's also what Joe was saying. Joe was saying in it's sort of like these pion spectra and the pion EPT and the pion multiplicity, but you can get them from the spectra. So in principle, these things are fully correlated. But I still argue that in a way, at least we like to include the integrated ones because they're a little bit more reliable. Also, we kind of put some lower weights on the high PT pions. We don't know them very well. Yeah, I mean, in principle, the correlations are taken into account. So it doesn't matter if we add them or not. These ones are a bit more accurate, so that's why we add them. It also looks nicer. We could try to leave them out. See what
I think you
happens.
should leave them out. I don't know, my main point is that I think there's some arbitrariness in how each observable is weighted. And it's a little naive to say that like just equal weighting to every point is exactly the right thing to do. There's a little bit of arbitrariness there about that.
Just be sure. For example, you mentioned about ET. There are so many things, so many points. You said for Bayesian analysis, they will fit it because there are so many pins. But in fact, if you even use a wider pin, your uncertainty will be smaller, so that it should be the same.
No, I was saying as an example, if you do it naively, it would really want to fit it. But since it's correlated, you see that it actually doesn't have a strong effect. If you repin them, it doesn't matter because for ET is very easy observable, so it's not statistics dominated. So it doesn't matter if you repin it, it's systematics dominated.
Sorry. So what is TET?
Yeah.
Sensitive to which parameters that it's mostly sensitive to?
It's the total transverse energy, so it scales basically like the multiplicity times the mean PT. So the multiplicity is really the norm, but also other things, and the mean PT is basically the Wilks viscosity. I mean, that's the first order, but then there are many other things. I have in the backup slides for every observable exactly what it's sensitive to. But if you ask later on, I can show. So okay, so that's then I think the last thing on the Bayesian thing. Oh yeah, no, okay. I'll show a little bit about oxygen and neon. So these problems of course you saw before, and now I also show you after this Bayesian things like what are the different bulk viscosities and shear viscosities for these particular settings. So now there's no uncertainty bands because the uncertainty band is really made from like not 10, but maybe a few thousand, and that kind of determines the uncertainty, the bulk viscosity and the shear viscosity. And yeah, so one reason I actually wanted to make this plot was I wanted to visually see that if you have like these small kind of structures, that you get a large bulk viscosity. If you have like very smooth structures, that you get a lower bulk viscosity. Yeah, so wow, I looked at it for a long time and didn't really see it. So it's a little bit unfortunate. What is true? Yeah, I don't know. It shifts also a lot. So I think that's one thing we actually concluded, that it's the height doesn't matter so much. It's really where you put it. So if you put it close to lower temperatures, it has a much bigger effect than if you put it at higher temperatures. So that's also why it's difficult to see. There should be a bit of this correlation. It's also true that, for instance, this one may have, but has a pretty, it's not that big of a bulk viscosity, and then you really see like this the mean PT. So it really overestimates the mean PT. you actually wonder a little bit, like, why does the Bayesian analysis not just put a bit more bulk viscosity to make it lower? That's not very hard to figure out. A lot of work. This one gets the slope slightly off. Most of them get it pretty good. Shear viscosity is similar story. So this is the V2 as function of centrality with like the data and these kind of things. What's also why I like this plot quite a lot is that I not only put like the real results from a high statistics run, really like 100,000 hydro events, but also the dashed line is the emulator. So you can really see like it's kind of a validation how well the emulator does. And in this case, for instance, you really see that there's a bit of a mistake in the emulator. So the emulator thinks it's doing quite a lot better than it actually does. So here, if we improve the emulator, that would improve the physics here. And also here for the shear viscosity. So your shear viscosity really overshoots a lot, but the emulator doesn't think so. It is true that this difference, that I already pointed out earlier on, it gives this wide band so that the uncertainty in the emulator does capture that. But okay, if you improve it, you really can improve the shear viscosity for this particular one. And here it undershoots, should have been higher.
What's involved in the emulator? What are all the bells and whistles?
Yeah, so it's really like these 1200 design points, of course, where you do the real computation. You do principal component analysis for all the things and the parameters. And then for all these principal components, for each one individually, you do this Gaussian process. So the Gaussian process, you need to train, right? So every parameter gets a certain length scale. It's very sensitive to the parameter. If that component is sensitive to that parameter or not. If it's very sensitive, the accuracy goes down. So if you, and then the Gaussian process gives you for that component a number and an uncertainty for each parameter point. You redo the principal components, and that's how you get your correlation matrix.
Is it true that for the size of V2, it's only sensitive to the average intervals? So it doesn't matter which shape you give. But I remember for EKRT, they do have these eta of different set of eta of s, and when they set the mean eta of s to different two, the results are identical to a fixed eta of s.
I can quickly, when we check these kind of things, and yeah, so you can take the backup slide. You can look at it for a long time. Yeah, so this is the V22, right? And I think, yeah, so that's the reason why we were looking at it for the same reason why we reparameterize it. So we have like eta over s average and eta over s slope. So you can see it directly, right? Because if you say it's only sensitive to the average eta over s, like Sean-Yves has a paper about it, this is of course true to first order approximation, right? If you look at like eta over s average, it's really this whole blue stuff, all the flow really depends very sensitively on average eta over s. But the next one is the slope. And well, you see also the other one. If it's completely green, there's no influence, but you see, especially the V3 here, has a lot of effect on slope. So it's also, of course, true that the slope is important because you spend more time at low temperatures. So it depends. Yeah. Okay. So that in that sense, this answer is not complete because it's not a weighted average. So we have yeah, it's just the average of the eta over s between 150 and 300 MeV. It spends more time at lower temperatures, so you should be a bit careful with this conclusion. Okay. Okay, I think this is this nucleon width, I mean, it really struck us. So I'll just say quickly, because it was also presented before by Govert, but this is the total lead cross section. So it's something between 7 and 9 barns, of course. And what was very interesting is that it wasn't measured until very recently, last April. And this is then the ALICE data point. And funnily enough, in this whole model, well, you have a collision or not. It doesn't depend on hydro. It doesn't depend on basically anything, right? If you have a collision or not, it only actually just in the model, but also in general, depends on these 4 parameters, which is the nucleon cross section, the nucleon width. Then we have the minimum distance between the internucleon things, which we impose in the Monte Carlo Glauber. And we put some normalization constant in our model, which is just actually, well, just by definition, a straight line. But it's an emulator result, but definitely we rescale the number of events by a parameter, and we try to fit that parameter and also link it to the cross section. But okay, the only takeaway is that this parameter only really sensitively actually depends on the nucleon width. Which also makes sense. I was already saying, like if you have these nucleons of 1.2 of a Gaussian, and these nucleons are huge. the total nucleon-nucleon cross-section is still the same. So it's always 67 millibars because it's the sigma GG and the collision probability is fitted. So if you have very big nucleons, they're very unlikely to interact. They're very transparent. But that doesn't mean that the lead-lead cross-section is the same. So if you have very large nucleons, just your lead nucleus get bigger, and you just get more peripheral collisions and well, relative to the number of central collisions. So that's also why this, why this cross-section matters a lot. And previously, so okay, I have that on the next slide. So there's the escape and Duke results. I put it in the backup, I think. But previously, what we had in triactum is basically this purple line, so the posterior of the width. So this is without the nucleus cross-section. So it's kind of one Fermi. And yeah, if you look back, then of course, if you're one Fermi, then you're really quite far off of this very precise result of 7.9 bars. So I was quite shocked about it. We also studied this for a long time. I told Howard several times, your code must be wrong. but no, code was right. And yeah, so what we then do, of course, first thing to do is kind of trivial, is this green one. So we just add the nucleus cross-section as an observable in all the data points. Also for PLED, by the way, that's a bit important because there are two of these cross-section measurements. And then naturally it goes down by a lot, actually, to 0.65, well, because it was inconsistent. But it also made us think a lot more, like especially, okay, I don't know if it's really inconsistent, right? I mean, you have this green one and this purple one, but it's quite a shocking change. And actually this 0.65 is still a bit too high. If you're still like 1.5 sigma off. And it made us wonder a little bit, like, do we trust the Bayesian analysis if you add one extra observable and it's inconsistent? So, and I think that the answer is a little bit that we should have been a little bit more careful. And so, okay, I put a whole story, you can maybe read it later, but in the end, we decided that it must, well, I think the experimental uncertainties are fine, although there is correlations. Most of these things are determined by the theoretical uncertainties. And we choose to kind of wait a little bit. So like the cross-section is a very robust observable. Theoretically, we trust to compute. I mean, it's a collision or no collision. It's very easy. Integrated observables are also unidentified and a little bit easier to compute, like the proton-kaon ratio in SMASH. It's not so, there's more theoretical uncertainty there. And that's why we give them weight 1/2. So we kind of multiply the uncertainty by a square root of 2. Which I think is theoretically motivated. I want to stress that, although there is these correlation things. So that's what we do. And if you do this, then observables that you trust more, they have more power. So that's why this width shifts even more to the left, to like more 0.55, like what I was showing you in a few slides ago. And yeah, so these are then the new fits, including the cross section. And yeah, so one thing I like to show is that I guess the zoom is not so fast. But on my screen it is very fast. So if you have no cross section, it looks like this. If you have this cross section, well, then it will change again. It looks like this. On the computer you can go back and forth quite often, but the lesson is a little bit like this width, the cross section is much smaller width than the other one, and the Bayesian kind of estimates. If you look at it by eye, you don't see which fit is much better than the other. I mean, obviously, if you include this cross section, the width is a bit smaller, and the Bayesian doesn't prefer that. So this fit is slightly worse than the one I just showed you. But it's hard to tell why, and that's also why I think we have to be a little bit careful and rethink this kind of global analysis of so many data points. Like, well, that's why we do this weighting. So that I think now with this weighting, for instance, the bulk viscosity is much less certain. But I think that's a realistic thing. So we kind of have to include this theoretical uncertainties because otherwise you're a bit too confident about your results.
Okay, can you compute like the base factor?
Yeah. So it's not so different. Like if you choose this width, well, I mean these are trivial, right? I mean the base factor between 0.9 and points the maximum. You just take the ratio, and that's the base factor.
Can you calibrate the width with PP collisions? Or is that something completely different?
The answer is that I don't really know, because well, we discussed this last week. There is like Trento is very similar to Pifia in this sense. Like Pifia also has an impact parameter dependence and also a Gaussian profile and also has an overlap function. And then with Govert, I don't know if he has any ideas about it. So we tried to look into Pifia, into the code. What was the width they used? Didn't figure it out. So the answer I think is yes, but we didn't manage. We thought about the same question. So we fixed this width, and then I really have to say much more about oxygen. Then this row observable we saw a few times really is much better than the red one. So it wasn't only true like what I was just showing you. Okay, that data maybe you didn't see very clearly, but this one got a lot better. And then well, in quark matter they always say it's new at quark matter, so it's new at INT. So with some we spent last week a few hours, and now we fixed the centrality. The selection, I got new atlas data that it's apples to apples. So the centrality selection makes a big difference, and well, it's almost too good to be true. So both of us are very happy. Good. Well, sorry about being so slow. Yeah. So now, of course, the oxygen and the neon story. So neon looks like a pinball, and oxygen a bit more spherical. It has its alpha clusters. So. Well, this nucleon width, but okay, then there's this question about the workshop was about, are heavy ion collisions sensitive to nuclear structure? The answer is obviously yes, but it's actually somewhat small effect, and we'll study it more carefully. The question is also like, are heavy ion collisions, do we need that precision? Historically, maybe not, but we really want to go there. That's why we do this Bayesian analysis, to be everywhere quite systematic about it. So okay, we also want to be systematic about nuclear structure, so we vary several approaches, parameter settings, like these 10 different settings. And the question we want to answer is a little bit like, do we need an isobar, like oxygen and neon? Yeah, so there's a lot of motivation about oxygen, like cosmic rays, smallest droplets. Okay, skip that, that's the fixed target mode we already had. So what we do is we have like 3 different oxygen nuclei. The 3PF is like 1976 Wood Saxon. This is the standard one. Then there's this variational Monte Carlo. Yeah, so it's kind of, and then there's the nuclear lattice effective field theory from Dean here. They are characteristically different, so that's also why it's quite an interesting question we find. So this is the 1-point density, right, of the charge density for these 3 profiles, or I think I only show, yeah, for these 3. And this is the 2-point interaction. And yeah, so it's really annoying. So the VMC gets, I think, the 1-point density completely wrong, and the NLAFT gets the 2-point correlation completely wrong. So we didn't quite know. Because yeah, so I think this is measured, so you really have to get the charge density right. That's kind of the first thing to get right. But okay, for instance, in the NLAFT, you actually have some positive nucleons like to sit on top of each other, whereas we kind of like this hardcore repulsion at around like 0.5 Fermi.
Is this a possibility that it could just be, are these sample nucleons? Could it be that they're putting on a grid size or something that you're getting this dip in the middle for VMC? Because this is one thing we noticed with Dean stuff when we used initially is we would get like a dip in the middle, and then that's what the smearing approach, because it was just like a finite spacing effect.
Yeah, they wouldn't have a grid.
Oh, this is not a grid?
Yeah, this is
Okay.
continued DMC.
That would be so true. Yeah. Okay. Also, is then the smearing? Do you say in your case you just get this right because of the smearing?
Yeah, yeah.
Okay. So maybe this is not as impressive as it looks like.
What's the interaction for the BMC? Did they vary the interaction at all?
Well, it's an advanced nuclear interaction.
It's just because at very short distances, I could imagine there's quite some dependence on the interaction.
Maybe Dean knows.
Through the BMC?
Yeah, it's
It's
AVG.
AVG. Yeah.
They didn't try anything else, like local cargo or something.
No, this is Diego Leonardoni's stuff.
But they don't have those. Yeah. But I could imagine that there might be some interaction, especially at the, between 0 and 1 for me.
Well, yeah. So, I mean, actually, these 2-point interactions, that looks reasonable to me. But okay, I mean, I'm not an expert at all.
I don't know what is reasonable at those short distances.
By
Below the size.
yeah, it depends on the nuclear species and spins, and yeah, well, that's fair. But they shouldn't sit exactly on opposite sides. It should be a hardcore nuclear repulsion.
But that's also something that's not observable, right? It's no such thing as an observable hardcore. You can always.
Wait, it's
transform
intuition.
it.
You cannot put 2 protons on top of each other.
Yeah, you have poly exclusion, but that's just anti-symmetry of the wave function, really. It's it's not actually article repulsion.
But it shows up in this plot. It's a correlation.
That's fair.
Well,
So
it depends on if you plot something, it depends on the operator, right? If you transform your direction, you can transform the operator, you can get the same physics, but the picture interpretation changes completely. This is why I think you have to be very careful at these very short distances to draw a conclusion that it really is that.
I'll hold this for discussion in the afternoon. I think. No, that is a very good question. I would like to discuss it.
I just want to, large correlations at 8 femtometer distance, why is that?
Yeah, Giuliano studied this quite a lot. It's a finite volume effect, I think. So if you find something here, then well, 8 Fermi sounds like a lot, but that's probably the size. I mean, it kind of has to, all of them do it.
So up and down, are these 2 oxygen nuclei, or is this the correlation
No,
within the same?
within the same one. So that's why
Really?
that's a finite volume effect. That if you have something here, you also have effect. Giuliano had a good explanation for it. It's a relatively trivial. There's not much physics there. Yeah. Well. I will be very interested to talk more about. Also to get like your ideas to vary these kind of things and get more problem. I mean, that was the idea, of course, to get like all of the state of the art, and then we got 2. So right. So we want to kind of understand a bit of the uncertainty. And it's already quite interesting. Like we compute this elliptic flow for central versus off central for these 3 cases where the Wood-Saxon maybe you have to ignore. But actually, so funnily enough, this VMC does the same as the Wood-Saxon exactly. And you see this NLEFT has a much higher V2 of especially for the central collisions. So that's, yeah, this is really quite a big effect. I would say it's like 12%. Yeah, so I'll show more about it also. Well, just with this VMC. So yeah, for instance, you cannot even distinguish it from this elliptic flow. I want to be much more systematic about it.
Hey, can I ask one question here
Sure.
for the first slide? Yeah, for this 3PF, what's the difference between this 3PF and the up size other 3PF? I'm not sure the parameters.
Yeah, the 1976 is the standard one you find in the Monte Carlo Glauber, I think, right? Yeah, it's the one everybody uses. I don't know the parameters on top of my head.
Yeah, but I can you go to the before slides? Yeah, there is some 3PF parameters with different W and neutron skin. The later slide, the 3PF is same as this, or it's different?
Yeah, okay. Yeah, that's a bit confusing. So indeed, so
Yeah.
so these are the plots we made. So we have like VMC, but we also have VMC 3PF. So that we fitted the VMC nuclear positions with the Wood-Saxon, so we get different parameters there. And then you see that this, for the 1-point density, actually fits the distribution very well. So you can use that if you only care about the 1-point density. But then the plot on the right shows that you completely miss out on the 2-point correlation, which makes sense because you don't use actual nucleon things. For this case, just ignore it. Yeah.
Okay, thanks.
Yeah, so okay, but yeah, so that's the important thing. So this of course was a kind of interesting plot, like, and I repeat it here for like what we call our map setting. So it's this one parameter setting, which is actually the maximum likelihood. And well, it looks like you can distinguish the two, right? So naively, you just go to LHC and you say, oh, measure this, and we know if VMC is right or NLEFT. But that's of course not true because this is just one parameter setting, and we want to be systematic about it. So what we did is we varied all the parameters here, and here we did it kind of 1 by 1, which I think, well, that gives a lot of insight in a way, right? I mean, if you keep everything fixed, but you double or half the shear viscosity, that's what's done here. And of course, we know if you double the shear viscosity, the V2 will be much lower. If you halve it, it will be much higher. And in this plot, you see very clearly that this nuclear structure effect is a relatively small effect. So the thing is, you get only one measurement from nature, and the message of this eta over S plots, and of course, you better know the shear viscosity very accurately, otherwise it doesn't matter. But okay, this is just by halving and doubling, and that's not necessarily realistic. But bulk viscosity, similar story. Here you could also say, well, okay, but the centrality dependence looks quite different, and that's also why this is maybe not. For instance, this sigma fluct I thought quite striking. Sigma fluct I talked about before. This is the fluctuations of the particles that you produce, and you see it looks very similar. Also, it doesn't depend on the off-central one, but at the central one, you see it has exactly the same effect. So if you double sigma flux, you really go from VMC to NLEFT. So this plot basically tells you that these differences in the nuclear structure is basically how many fluctuations you have. So that's also kind of related a little bit to a lot of people are asking, are we sensitive to the short range correlations? Well, these are different short range correlations, but you can compensate it by other fluctuations. So if you so these are nucleon fluctuations and not position. So these things are a little bit interchangeable. So I think we're sensitive to it, but only if you know the sigma flux very accurately, say from that lead collisions. The width I also put here also has a very big effect because you smooth things out a lot. So it's kind of coming back to that. There's these Trento parameters I don't have time to go into now. And then it's good for reference, so you can just look at the slides later. I put all the observables you looked at here, the multiplicity. So the nuclear structure has very mild effects. So multiplicity, if the ratios doesn't depend for the nuclear structure, actually, if you change these Trento parameters, matters a lot. So multiplicity, you definitely don't want to look at if you want to figure out nuclear structure. For the mean BT is probably more or less the same, so not much effect. And the build viscosity has a very big effect. The amount is not a very good observable. Which is, wow, this is more, I guess it's also partly for Giuliano. So there's this correlation between V2 and mean BT, this rho observable I showed before. Many people talked about it, and it's conjectured to be very good observable for everything. And it has quite some differences between like VMC and NLEFT, so it's significant. But yeah, for instance, here the sigma flux doesn't matter, but here the eta over S has the similar effect of shifting this rho observable from one to the other. So you have to be a bit careful. The width, you also better understand this kind of this systematic analysis, looking how observables change as function of all these parameters. But okay, that's maybe still not systematic enough. So can we do it more systematically? Okay, because what do we know about observables? The observables, also viscosities and this Q and P, they're highly correlated. So I can say, well, what happens if you double the viscosity? But if you double the viscosity, you also need to change the width, the Trento parameter, the sigma flux, and all those kind of things because they're correlated. And this is done by using these 10 parameter settings I showed before. So this is a kind of the probable parameter settings, and that really scans consistently the space of the posterior. And yeah, and then you just compute the average and one standard deviation uncertainty. So that's overlaid here. I only did it for the VMC because, okay, that should be the band. The width of the band should be similar for VMC than for NLEFT, so we'll just shift it. And indeed, you see that, well, okay, so this is, I think, very good news because the width of this band is very comparable to the difference between the nuclear structure. So it really kind of seems that the systematic uncertainty we have, if this, well, you trust the reactum, I guess, is comparable to the uncertainty we have from the nuclear structure. If you look at only these two, so that's also why we need more. And well, here the ratio is also quite important. I'll show it a little bit more, but this green band is the 1% band. So you see that the systematic uncertainty is really quite large, it's almost 10%, but also for nuclear structure. And we're not really at the, if we want to go to percent level accuracy, which of course we want, yeah, you need to understand a bit better both perhaps. But the nuclear structure you also definitely need to understand, otherwise you don't get much leverage to understand more about things like shear viscosity. And then, of course, the question we want to answer is, does it help if you then include neon? And unfortunately, we only have like, I guess, a different kind of EFT for neon. We're trying to get, so we don't have an apples to apples comparison. I think there's not a single computation which has nucleon configurations for both neon and oxygen. So it's a request. And I think, so it's a neon we got from the group of Benjamin Bali. And they're working on oxygen, so we will get this apples to apples comparison. I think that's very important also for these ratios, right? Because it's now you're just plotting things in a way, although the spread kind of tells you it. So neon has a much larger V2 over the whole range, which is really because of this pinball shape, right? So it's easy to understand. Still, this is not systematic.
Question here.
Yeah.
So I'm confused about this pin shape thing. Because then from a naive argument, what we would say, if you have said you have a rotational band with odd and even spins, but neon 20 doesn't have that. It's 0, 2, 4 plus, it doesn't have 0, 1, 2, 3, 4. So that's unexpected, that picture, at least. Yeah. Normally you would say, if you rotate it by pi, you get back to the old nucleus. And not...
We were talking about that in the second week with Benjamin. Okay, those are his calculations. And I think what he's saying is when So if you think about, right, you have your neon 20, you pull one of the alpha clusters far away, then you have sort of an A and C for an alpha with an oxygen 16. So he's seeing a little bit of that in his configuration. Yeah, that's all that is.
Yeah, that's all. It's a computation, so it matches the intuition, but okay, I mean, these are cartoons, I guess. Well, these are the actual, I think, configurations from well, these are VFC, I guess, but, from oxygen. So if you actually plot the nucleon from oxygen, you don't see these 4 alphas, you don't see this pinball. It's just if you average it very carefully, you do, right? I mean, if you look at the nuclei, you kind of well, you put it at the center of mass, then you find like the proper rotation axis, you rotate it, then you average over all these profiles, then you see it. That's actual computation, but I don't have the plot at the moment. Okay, so we will of course want to do this systematically as well, because the systematic uncertainties are very important. So that's again this one. So this blue band is a systematic band I showed before, and the same one for neon with the same 10 parameter settings. And yeah, so okay, I mean, there's I guess a definite prediction that quite likely neon will be higher than, but within the systematics, of course, these are hard to distinguish even, right? Because it's a little bit uncertain. But then of course the whole idea of these isobars is that you can take the ratio. So this is oxygen and neon independently, and here's the ratio of oxygen over neon. And well, obviously oxygen is smaller by like 20%, and more so at central ones because you kind of select the nuclear structure, and then less so. But the important thing is this arrow. So if you take the ratio and you look at the uncertainty, which is the same systematic uncertainty at the 20 to 30% region, you're within the 1% band. So yeah, if you measure the V2 of oxygen and neon, and okay, and there's so much uncertainty, like 7%, not so clear how much you really learn. But if you take the ratio, then at least like the uncertainty because of shear viscosity, because of all these things. Yeah, so here, yeah, if you just have oxygen, you have so much uncertainty in the shear viscosity that you don't maybe learn all that much. But here, like for the nuclear structure point of view, that all cancels and you really have a very accurate prediction. And I have to stress that this is, of course, for the same nuclear structure. I mean, it's very obvious that if you change the nuclear structure of neon or oxygen and has a different shape, then this curve will change and you can distinguish it because it's 1% level accurate. Was something that surprised me a little bit, and that's why I put this ultracentral plot, and that's what we did with this entropy acceptance things, right? So these are 100 million events in the end, so we can go to a centrality class of like 0.01%, so it's like 1 in 10,000 events, and it's really kind of filled quite well. It's really, well, statistical error is sizable, but not so much. Actually, yeah, so these are statistical errors and systematic uncertainties. So what of course happens if the statistical uncertainty is very big, then you don't see the systematic anymore. It will just be dominated by statistics. But here you see, because I also show it, that this is still systematic dominated. It's not because of the statistical uncertainty. And which is, yeah, so in LAT, I think we always say in the isobars, you really have to go to ultracentral, 0.1%, and you see the nuclear structure. And what this plot shows is that it's not true. So here actually there's a 7% systematic uncertainty, and the sweet spot is between 20 to 30%. It's kind of interesting, and you see it already from this plot, because in the end you take the ratio, and this band is much wider than this band, so it can never cancel. So the oxygen for ultracentral has for some reason a much larger uncertainty than the neon for ultracentral collisions. Yeah, I mean, I guess it's obvious, but these are really 10 lines, the red one and the blue one. You have to get this ratio, you divide line by line, right? And that's why this uncertainty cancels. Yeah, so that could be an expensive fact, because yeah, the fact is that these oxygen collisions, you don't learn much. You need the neon if you want to know more about nuclear structure, I'm afraid. And then once you know more about nuclear structure, of course, it will be very interesting, because then you can measure this very accurately, and then you can constrain maybe your model.
Have you looked into the ratios of multiparticle cumulants? Because a lot of this would cancel a lot of the medium effects would be done.
Yeah, so I talked with you about it. So the problem is that these are relatively low multiplicity events. So this V24 and V44, I mean, so we talked about it, and you integrate this freeze-out surface with some Lagrange thing.
I see, because you're
And
statistics.
well, if you want to do it completely, so triactum, so we never did this kind of approximations. So the problem is like V44, for instance, we definitely computed it, but for 100 million events, you don't get that far. So you can use this Lagrangian integral, like the freeze-out surface, but we don't like to do that, because if we do the approximation of the integral, then I always want to first check that it gives the right answer. but then you have conservation of misery because to check it, you need the answer already. So we cannot do V44 because we don't have a method. Well, your approximation, we need to verify it because these are low multiplicity events over lead maybe it works, but even
Yeah,
for lead we
we-
have problems getting V44.
Even V24, V22, I mean, that should be easier to get. And that should cancel like a lot of your median effect.
Yeah, even V24 is difficult. I mean, I
Makes
think
sure
I
you do it.
mostly showed everything that we could do because I plotted all of this. This one is mostly the row correlator is the, well, V24 maybe we can do.
Especially, you always do the uncertainty after you've taken the ratio because the correlative uncertainties there. The
Not
correlator-
really, because the V22 has very, very small statistical uncertainties, but V24 has much larger statistical
Right,
uncertainty. So
but-
the statistical uncertainty doesn't cancel.
Trust me, I've done this separately and I've done them together and it does make a difference.
But the V24 or V22 ratio, you're supposed to do event class average ratios, right? You're not supposed to take the ratio event by event and an average.
No, not event by event, but what you do in centrality bins, there's a way to take the total ratio. So Jenny has done this for Atlas, in fact, where you've done it over the ratio. And so you get this canceling of the errors. I can show you the paper.
You basically treat these, the ratio of local as observable, and then you do all the events as mathematic uncertainty. So that's such a.
Systematic cancels, but the V24 statistic dominated. So it
Because
doesn't
otherwise,
cancel.
they are partially correlated. You have to do a propagation.
But the statistical uncertainty doesn't cancel.
No, some of your.
Not completely, but it is correlated.
But the V22 is negligible. I mean, the V22 is extremely accurate, right? That's,
No, but you still, I've done this. I can tell you, it definitely makes a difference.
Right, Jackie, I'm not sure if I agree with this. I mean, for the proposal of V22 divided by V24 or the other way around. Because if V22 and V24 have similar sensitivity to this nuclear structure, you might actually lose the information of such a sensitivity.
That is,
I can imagine that the dependence on viscosity will be cancelled out.
Sure.
But then you also lose some of the information from nuclear structure.
that is entirely possible.
I don't think so.
You have, it might be different information, I would say.
The nuclear structure is exactly changing the fluctuation in
So
flow.
that's
And its
correct.
ratio is actually kind of isolating how much does V2 fluctuate.
So that's why we have for Xenon, we are doing V22 and V24, and then try to calculate mean V2 and sigma V2
Mhm.
to isolate the
That's it.
dependence on the fluctuation and the shape. But when you do the ratio, you might cancel.
How many particles do you have in these ultracentral ones?
yeah, not well. Okay, I didn't plot the also central one, but of course for central ones we have 200 and then it grows more on the log scale. It still keeps on growing in straight line with different slopes. So it grows a bit more slowly. Typically, very ultracentral, I think you get like 25% extra. It's like 250 yen ether charge. Yeah, this row observable, for instance, you can do a similar thing, but here you don't take the ratio, you take the difference. So it's quite funny. I mean, they overlap, but if you take the difference, I took all the 10 bands individually. If you're really very interested and want to zoom in, then you get some definite prediction for the row to difference, and it might depend again on the nuclear structure. Well, so yeah, the nuclear wave was exciting, and then oxygen summer 2024, and we might, yeah, I think if we want to gain the most of this oxygen run from a flow point of view, we might have to start a campaign now for neon to get physics at the percent level science. And it would of course be great. So that's the conclusion.
Instead of using isobars, is it possible to use isotopes, sort of consecutive isotopes? There are 3 stable neon isotopes, and none of them are that rare. Neon 20, 21, 22. If you did 20, 22, 20, and average those and compare with 21, you can see then a lot of cancellations.
Yeah, so Yeah, I mean, I think there's not, in principle, no problems, right? I mean, I don't think this isobar story, I mean, I think for me, xenon and lead are isobars. You have to look at order of magnitude, and then most of these things cancel.
Yeah.
Like if the shape is more or less the same, then a lot of these effects will cancel. So different neon isobars I'm not against. We discussed a lot with CMS and Alice, and I'm more optimistic about this than they are, that we can get like 2 days of LHC running time. Well, then I guess it will be neon 20. Although if there are very strong arguments to do like neon 22 or 24, I think that's possible. But to do several, so for the injection department, they definitely need like 6 weeks between 2 runs.
Okay.
So
Would that be any easier if
you
they're,
cannot do it like go.
would that be any easier if they were like isotopes, nearby isotopes?
So I don't think it
Would
matters.
that, would that,
For us,
that
it
would
doesn't
reduce,
matter.
no, it would reduce the amount of time they need to.
I think they need to clean everything and restart it. They're not, it's not like at Rick, I think they can change much faster. That's what they told me. So that's also why I think, so this will be 2024, but I think there is an option to do the same thing in 2025. But only one, I think. Well, that seems to be pushing it already. I'm optimistic. But yeah, so when we put these different neon ones, so that sounds, I'm not fixed on neon 20. If there's good argument.
Yeah, especially if something interesting happens with the structure, you change.
But not to change, not to do all of them, not to do a whole row, because I think that's very expensive.
Yeah.
It's already very expensive. to be
All the idea we like to have to push in Alice is we try to go for general interest for example, also hard fault people and also CME. You remember the isobar round was motivated by the CME studies. If we can also involve more people, then it will be easier. Easy in Alice. For CMS and Atlas, they are heavily dominated by the flow activities, so it's easy to get those. For Alice, we have to make those people.
Yeah, so with INT, I mean, I didn't think much about it, but last week we did some small computation of zirconium and ruthenium, and that the encode is very good. The number of binary collisions, we expect like 8% more hard probes for zirconium. So that's like very interesting. That's we didn't repeat that here, although yeah, it's just one press of the button. I can plot. That's a good idea. Man. Yeah, oxygen 18 we can also, that's maybe also, I don't know.
What about carbon 12?
So gases are much easier, so they just inject it. Okay. Well, one thing, okay, I always say that the SMOG2 is very interesting, and it's always true, but okay, there might be much easier to do like lead neon with different neon isotopes. That's I think at SMOG2 they can get a lot of luminosity and also a wide variety of things. It's just a question if they can analyze.
What would be interesting for me, if, but carbon 14 and nitrogen 14 comparison would be very interesting. Because the beta decay is very suppressed, and that could be a difference in nuclear structure, and it's not really understood what that difference is.
When the system size is getting smaller, it's
Yeah.
no challenge of to
Things get a little more dicey.
But if you're doing oxygen, just drop down to.
Well, even oxygen, I don't know how well do we understand the,
Yeah,
how much
it's
non-flow will be,
Right.
how well we can
So
isolate.
all of
like,
these things get much
flow.
easier in run 4. Like if you look at the end of the 2030s, I think there's a lot more possible.
Yeah.
And also carbon, I mean, they should be able to do that. Although twice, you need a pure sample of carbon 14.
Yeah, that may be hard. But,
Just real quick, so this VMC that you had, like you have discrete configurations of nuclei that you have from them. That's what you're using. How many? Like, how did you get so many events then?
No, we just have
Just take like a few nuclei and rotate them a bunch of different ways? Or?
Yeah, but I somewhat doubt that could be, but
How many
like
do you have?
10,000.
10,000
But then of
nuclei?
course you rotate them. Well, they are themselves rotated, and also the impact parameter, and they're both rotated. So there are 3 degrees of freedom. It's the impact parameter and the 2 rotations, which are both actually. So there's like 5 degrees of freedom. So the question is if you get enough randomness.
If there's any kind of bias
But if you have
for some-
10,000 of these configurations,
That's
I mean, obviously we
probably fine.
didn't chance. I mean, of course, you have to be a bit
Like how
careful.
many
We're
of-
looking at one every 10,000 events.
So to be fair, when we
So-
did this with these, we had like 15,000 configurations, we ran in Trento, so I think it's really the same.
It is the same, but
Yeah.
I mean,
But then you have
okay, you
to-
didn't plot into a point of 1%.
No, we didn't, I'm saying just for this like dip in December. part.
Here, it definitely doesn't matter,
Oh,
but
yeah,
for
that's-
this, there is a bit of a, you have to be careful when you go to very special
Yeah.
events, that very special effects might show up. There's some about it, but we didn't check it.
I don't know if my question should be discussed now or in the afternoon, but I'm just curious for Jackie or anyone. For the energy loss, right? If you think of the energy loss in oxygen or neon, because the size will be similar, the shape might matter.
Yeah.
If you talk about past energy, kind of energy loss, well, is there any way to calculate it to see, okay, neon has a larger energy loss, we go to some direction?
So we did actually study, we didn't do it with jets, we did it with heavy flavor, and we put in deformed xenon, so we haven't looked at a light nuclei. But we didn't see anything in RA, but we did see differences in the V2 of heavy flavor. And so you can see the single difference there. And then I think you're doing a study now with Yenji, right? You were on that,
Yeah.
that he talked about last week, where he was trying to get some pathway dependence. Which one
Yeah,
was it? It was
we
the-
just integrate the temperature cube to it, so we don't really have like either heavy flavor or jets Monte Carlo, but well, that's much longer term, but like the
Yeah.
path length depends, especially if you do like event shape engineering or you look at in-plane, out-plane, like the correlations, should be quite straightforward to see.
I do have a student that will eventually do this, but it might take a while, at least just starting, so, he's still writing the jet code, so. let's see. But it's definitely like something you work, I'm assuming other groups are thinking about this too, because with oxygen is way better for jets because you might actually have real centrality. And that's always the issue.
It's definitely right. Other questions? We're hungry.
Yeah.
Let's thank Will again.